Sup, Miss Danny? Yo, can you guys hear me? I can't hear you.
What's up, people? You don't smell like cat. You probably do smell like cat, Michael. We were at Hillcrest at the apple orchard this weekend, and I had a couple goats, and a cow, and a rabbit, and a kitten. And I came home, and he was just like, "No, lady." Hey, Kai, what's up?
Hey, Miss Danny. I am
girl.
again Nanny.
Good to see you.
I'm gonna make some eggs while we're on the phone.
All right, that works. Let's see if we have any volume over here. Let's issue with that.
On that sandwich.
It's turkey, cheese, and mustard.
No man.
Mustard?
And also
Mustard's
cheese
good.
on
I've
a
actually
cold-
discovered this.
Wait, hold on. Cheese on a cold sandwich.
I generally heat it up. We have
All right.
on time.
Cole's gonna give us all of his sandwich recipes or whatever.
Hey.
Okay, so it's kind of a little bit of a smaller group today, but we're going to get bigger soon because I saw Sydney's mom said this morning she's going to come back on the 13th. So yay!
Wait, isn't Sydney part of our group?
Maybe.
I think she's
No.
part of our group.
No, she's online. She's been online all so far.
Yes, but she would be.
She would be, yeah. But by then we'll be in second quarter, so it'll be different anyway. All right, so we did.
Teams would change.
Yeah, teams will be changing. Is she in here? Come in. I lost.
Hey, Miss Danny.
Oh, she's back. Okay.
Miss Danny.
Yes, ma'am.
I think I could probably come back next semester.
Next semester or next quarter? Next semester?
Next semester, spring, because next
Okay.
quarter, I'll be working the election and then nannying a bunch.
Cool.
But next spring,
Yeah.
the next semester, my kids should be in school by then.
Okay, cool.
So I think I can come back. So yeah.
All right. She's hoping to come back next semester because she's working the election and then I don't know, bunch of stuff going on, and she's hoping everything will be straightened out by then. That would be cool. All right, so I did put this in a slideshow for you guys. Are slideshows helpful when you're online? I hope, yeah, I think they are, so that's why I do them, because I think they help a bit. But if they don't, then we don't need to bother. All right, no, don't tell me that. Don't, okay, whatever, go away. And now I need to
Are you screen sharing? Yeah.
Yeah, well, it didn't, thought I tapped it, but I didn't tap it. I have to open that first so that it goes straight to here. So there we go. There they are. All right, so we're gonna do our elements of the periodic table, and we're talking this time about trends, which is what this lab was about. So Kai, if you're gonna do this lab on your own, yeah, you and Ivy should do it together, and you're probably gonna lose your minds about halfway through because it's a giant logic puzzle.
Good luck.
Alex, you may want to find another person to bounce your thoughts off of because it's definitely tricky. Yeah, other Alex. Yeah, so it's a giant logic puzzle, and
Which is very fun.
I think it's fun. Alex thinks it's fun. Bailey wasn't so sure. So I actually have 2 different apps with logic puzzles on my phone. I like them, but only if I really want to think. Like if I don't want to think, I want to do something mindless, I am not doing a logic puzzle. All right, phones. Okay, so we're gonna see if this works, because if it doesn't, I'm gonna have to do it separately because the sound wasn't working for me earlier. So our favorite dude here, this Professor Dave guy, yes, he didn't want to go. I don't know why he didn't want to go, but he looks like Jesus. Yeah, no, he's Professor Dave, and he's super cool. I really like him. And he does great little compact reviews. So that's kind of why I wanted to show his thing. I cannot type today or any day, as you guys know. Where'd he go? Where are you? Here he is. Now let's see if we can actually see it or hear it. Okay, Kai, can you hear that?
Hear what?
Okay.
Wait, do it again. Am I on the TV?
Extra help on the go.
That makes me feel weird.
We've got an expert's explanation on how to solve it. With 30 minutes.
Okay, here he is.
Electron affinity.
Can I hear what, Miss Danny?
All of
Oh,
this.
she can't hear him.
Let's check comprehension.
I
on.
don't know what you're talking about when it comes
Yep,
to what
hold
I'm
on.
doing now.
I gotta fix him here. I don't know why he doesn't want to work with me, but hold on.
He looks like Jesus.
Okay, so you can't see that guy. All right, but I still need to share you over to this other screen because it gets weird like that. I thought you were drinking wine for a minute there. I was like, wow. Doesn't it look like white
No.
wine in a glass, or is it just me? It could just be me.
Nope.
All right, so here we go.
It's eggs.
We're gonna watch Professor Dave.
Dave, let's talk about the periodic table.
This is a nice summary.
Pretty much everyone knows what this is, even if they don't know much about chemistry. It's the periodic table of the elements, which at first seems like a random arrangement of substances, most of which sounds strange in form. But the way the elements are arranged reveals many beautiful patterns that tell us about how nature operates. In the mid-1800s, lots of chemists were trying to come up with a way to depict all the elements in table form, and many different formats were proposed. But it was the one by Dmitry Mendeleev that stuck, because of how well it correlates data, as well as its predictive powers.
Piercing stare.
He arranged the elements into rows called periods and columns called groups. Elements that had similar behavior were put in groups together, which helped to correlate existing data. And it also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in these spots, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected, and now we have all the metals, metalloids, and non-metals organized nicely. It wasn't known at the time, but the reason elements in the same group behave really is because they have the same number of valence electrons. Look at group 1, for example. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and n increases, you gain a shell each time, but whichever is the outermost shell, there is only one electron in it. Every element in group 2 has 2 electrons in its outermost shell, and so forth. This simple fact determines many characteristics about each element in ways we will continue to see as we learn more chemistry. There are some periodic trends that we can recognize when we look at the table. The first one is atomic radius, or the size of the atom. As we proceed downwards on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell, and each element to the right has one more proton in the nucleus than the last. So there is a stronger electromagnetic attraction felt by the electrons, and the radius shrinks. That means overall, atomic radius increases going this way on the periodic table. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away makes it smaller. Ions with the same electron configuration will have their radii decrease as the atomic number increases. Next, we look at ionization energy. This is the energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electrons to the protons drops off very quickly with distance. So the farther away an electron is from the nucleus, the easier it is to pull it away. This means the ionization energy trend is precisely the opposite of the atomic radius trend. Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus, and atoms like to have their outermost shell completely full. Losing the electron means this shell is gone, and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus,
Can't see.
and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium. So the ionization energy increases going this way on the periodic table. Elements can have successive ionization energies for removing more than one electron. A second ionization energy will always be greater than the first and continue to increase from there, since the more electrons you remove, the less stable the atom becomes. An element will have a huge jump in ionization energy after you take the last one in a shell, because then you jump to the noble gas electron configuration from the previous shell, which is full, so it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look, for example, at the second row. From lithium to neon, the ionization energy should increase each time we add a proton to the nucleus and the radius contracts a little. But something like oxygen, which dips downwards from nitrogen's ionization energy, does so because of orbital symmetry. Here is nitrogen's orbital diagram, as well as oxygen's. Notice that nitrogen's 2p orbitals are precisely half full. This gives nitrogen a special stability, just like elements that have a full outermost shell. If nitrogen loses an electron, it loses that special stability. But if oxygen loses an electron, it will gain that special stability. That's why oxygen's ionization energy is a little bit lower than nitrogen's, even though oxygen has one additional proton. All deviations from the ionization energy trend can be explained by discrepancies in orbital symmetry, like this one. Next, we will look at electron affinity. This is exactly the opposite of ionization energy, since ionization energy is how much energy you need to remove an electron, and electron affinity tells us how much an atom wants to gain an electron. Disregarding the noble gases, as their shells are full, electron affinity increases this way. Fluorine has the highest electron affinity because if it gains one electron, it will have a full shell, or a noble gas electron configuration. Looking at the opposite corner, these elements don't want to gain electrons. They would rather lose them. Exceptions to this trend happen for exactly the same reasons as the exceptions to the ionization energy trend. Lastly, we want to look at electronegativity. This is the ability of an atom to hold electrons tightly. It will increase this way because a smaller atom like fluorine with more protons for its energy level, or a higher effective nuclear charge, will hold electrons best. Again, we will disregard the noble gases for this trend. Electronegativity will be important in the next clip where we learn about chemical bonds. So the trends to remember are atomic radius, which goes this way, as well as ionization energy, electron affinity, and electronegativity, which all go this way. Let's check comprehension.
that would take a few minutes. So. I do like this dude. He's fun. He really is. Professor Dave, he's even got a song. I mean, I don't have a song. Who's gonna write a song for me?
Professor Dave.
Professor Dave. Professor Dave is fun. Oh, y'all, I'm so punchy. I swear. So I was telling the younger group, I actually got I got 3 fillings yesterday, and I had this long conversation with the dentist about why he prefers gold over amalgam and composite. And we had this fascinating discussion about how gold is not reactive with anything in the human body, and it's also not why aren't you moving? And it's also not reactive with any bacteria or anything like that, and it wears down at the same rate as your enamel. Fascinating. Why doesn't this go?
That's why he uses
Ozzy, yes.
That's why he does. Yes, yes, yes. So, all right. So looking at this. So these were from your notes. So the amount of energy, and Professor Dave just discussed this, the amount of energy needed to remove an electron from a specific atom is called what?
ionization.
That's right. That's ionization energy. So what is half the distance from center to center of 2 like atoms bonded together?
Bond radius.
Right, atomic radius. All right, so the energy change that occurs when a neutral atom gains an electron. Whoops, I clicked it earlier because I was trying to move this. Yeah, so that's electron affinity. So ionization energy is about, compare ionization energy and electron affinity, or contrast them. Somebody do that for me.
Ionization energy is how much it takes to remove an electron to make it bond with another.
Mhm.
Affinity is how much it takes to bend to bond to.
Bond to, yeah.
together,
Together. Okay, yeah. So there you go. Ionization energy is about losing electrons. Electron affinity is about gaining electrons. You heard the word affinity before? When somebody has an affinity for something, it's something they really like, they want to spend time with. So they really want. So you think about it that way. They really want the electron. So what is the numerical value that reflects how much an atom in a molecule attracts electrons? Yeah,
Electronegativity.
that's electronegativity, right? Because electrons are always negatively charged. So
Electron.
it's right, yeah. Electron negativity is like right there in the, yep. And sometimes they take out the N and make it like a 1-word thing. You know,
Yeah, that's what I have.
you can do either way. As a nuclear charge increases across a period, the effective nuclear charge what? Increases, pulling electrons closer to the nucleus. And what happens then to the size of the atom? Decreases, right? That makes sense. All right, so then tell me about these. So which has the largest atomic radius?
D.
D, indium.
Yeah.
Good. And we have it back there. Where is it? It's over this way. Yep. All right. And then how about which of the following has the smallest ionization energy?
Nitrogen. Oh, vacuum.
So why is it potassium?
Yeah.
Ionization energy. Where's the,
It's closer to the top.
Here you go.
one.
closer to the top corner. So we're looking for things that go in there, right? Okay, and then so our last one, you see, right? So the following element has the largest electronegativity, chlorine. Remember that so I was telling the juniors today, when you look at the periodic table and you're looking at the noble gases on the far right, you can think of them as, you can think of the word noble or whatever, it helps you remember, but they're very aloof, right? They're very aloof. They don't need anyone else in their life. They're perfect. I don't know.
One or two.
Aloof. They're very aloof. They're very noble. They're very snooty. They don't need anything else. Their plate is full, right? They have all their electrons. All their energy levels are full. They don't have anything in valence that's floating around waiting for a buddy. But if you want to know like who the real troublemakers are, it's that halogen column. So that's the fluorine, chlorine, bromine, iodine, those guys. They are really, really, really troublemakers. They react with everybody. And then if you think of the guys over there with the alkali metals, those dudes are the ones that you don't ever see, you don't find by themselves very often. They usually are with somebody else. They're usually joined at the hip. So sometimes it almost helps to give them, I found it helps to give them almost personalities. You can kind of understand how they interact. You know, if you think of them like,
Miss Danny, you are
Yeah.
describing like half the guys in my life.
you know, I think you might be at something there. She said, Ethan says, oh Lord, just so you know. She said, I'm describing half the guys in her life. Ah, I miss you. Okay, so explain why the exact size of an atom is difficult to determine. Yeah, Cole, what have you got?
Preset boundary because of the electron cloud they have.
Right. Okay. So the model is based on finding your electron at a specific location. So you remember a couple weeks ago when we were putting up electron clouds, orbitals in different shapes, and we built one on top of another. And I said, you know, it's not really that the orbital's that shape, but you're likely to find it in that area. So as you move further away from the nucleus, your probability of finding that electron in that cloud-shaped area becomes less and less. So not a well-defined boundary. Yeah, hanging out in the closet, you know. So which metal has a larger radius, lithium or sodium, and why?
Because that's the way the direction goes.
That's the way the direction goes?
Sodium, because it's lower down the period, or lower down the group.
Yeah, it has one more energy level too. If you remember, if you're going horizontally, you add an energy level each time. Whereas if you're going down the column vertically, you're keeping the same number of valence electrons in each group, but as you go this way, you add an energy level each time, right? All right, somebody want to try and explain electron shielding? Okay, Cole, you want to go for it?
Electron shielding is the shielding of outer electrons using the inner electrons from the nucleus. Like I think it's using their electromagnetic field.
Yeah, so
How do we get completely different answers?
it's, okay, so no, you're on the right track. So it's the reduction of the attractive force between the nucleus and the outermost electrons
That is literally word for word.
due to the cancellation of some of the positive charge by the negative charge. So if you're looking at an atom and you've got your positive charges and your negative charges, your positive charges in the nucleus and your negative charges extending out from there, and then you've got your valence. The negative charges in between the nucleus and the valence are canceling out some of that positive charge, right? Because they're balancing each other out. So there is some shielding that allows the valence electrons to have a little less attraction to the nucleus, which is what allows them to become ions, right? They bump off an electron or gain one or however it goes. So because they are less attractive than the ones that are closer to it, they're further away. So how about this one? Explain the large decrease in atomic radii as you move across a period from group 1 to group 14. Why does the radii decrease? You're adding more electrons, same number of shells, right? If you're staying in a period.
Oh, because there's more protons that are pulled farther close to each other.
There's more, say again?
Protons that are pulled close to each other.
Right, so there's the protons and electrons. Basically what you've got is, it didn't give me that answer. Okay, so yeah, wrong answer there. I'm gonna ignore that one. So yes, you've got more electrons and protons. There's still a balanced amount, but there's pull to the center, right? Because they're being attracted. So as you go across, you're getting a greater pull because you have even more positives and even more negatives. So even though you have the same number of shells as you go along, so your shell stays the same, but your attractive force gets stronger, which shrinks the radius of the atom. I don't know why that one didn't. You know why? Because this is where it didn't save on me yesterday. Okay, well, all right, so this one was right. I wanted to check it because it was getting kind of weird on me yesterday. It stopped functioning in the middle of my trying to put this together. So explain why ionization energies tend to decrease. So this is because as you go further down a group, so this way in the periodic table, the further away the valence electrons are from the nucleus, right? Same number of shells, but you're getting more and more shells as you're going down, right? You're adding a shell each time. So they're getting further and further from the nucleus. Same number of valence electrons, more shells. The electron's attraction to the nucleus is described by Coulomb's law, which states that force varies according to the inverse square of distance from the nucleus. Well, there's your math problem. But your concept is that you're getting further and further away from the nucleus with each time you add a shell, right? So your ionization energy is going to decrease because the pull from the negative charges in the outer shell to the center is not as strong because you're further away, which makes it easier to take away an electron. All right. So, hi. Who's on a phone call? Explain the large increase in electron negativity as you move across a period. You want to go, Cole, Michael, somebody? Cole?
That's what Michael and I got, yeah. The effective nuclear charge increases across a period. Is this, yeah, as this increases as this increase, electrons are attracted more from it.
Okay. Anybody have anything different?
I got that from the book.
Yeah. All right. So as you move across a period, each atom is going to have one more proton, right? As you're moving across, and one more electron, but in the same energy level as the one before it, because the energy levels stay the same going this way, but you're adding protons and electrons. So because the electron shielding isn't going to change, the nuclear charge increase across the period attracts the electrons more strongly. Does that make sense? You have to kind of, a lot of it's visualization. A lot of this is visualization because it's like impossible to model it in a way that doesn't mess up the concept. So you have to kind of imagine in your head, okay, I'm going this way, same number of shells, but I'm adding more electrons. So how about these? These are your trends again. So this is pretty straightforward. Ionization energy from left to right.
Increases.
Okay, and down.
Decreases.
All right, somebody else tell me, atomic radius. From left to right. Decrease. I heard it quietly. All right, so then what happens going down? Increase, right, all right, good. Electronegativity, well, how about that going left to right? Decreases. How about ionic side? Okay, and there. These were perfectly inverse, weren't they? It was such a nice little pattern. I love it when things like that happen. Yay. So here again is the trend chart that we had up during lab. So for those of you who haven't done this lab yet, enjoy. You're going to want this out in front of you as well as the periodic table. And it's a big logic problem, but you have to know these trends in order to make sense of it, right? And wasn't there something that wasn't on here? What was the one that wasn't on here? It was.
Was it?
It was M and C. M and C.
No, not which letters. There was a trend that wasn't on here. Reactivity, that's right, reactivity. Yeah, you're gonna want one that has reactivity on it. All right, so now I gotta go do this again because it disappeared on me. I don't know why this thing doesn't want to work today. Why are you going to Wix? I did not say to go to Wix. You dippy thing. Oh, it helps if I would have stayed in YouTube because I'm not paying attention. Hold on. Gosh. I don't know who this dude is. Okay, here we go. So this is a shorter one, but it's Neil deGrasse Tyson.
Came from. To understand their origin.
Oh no, the other one was Neil deGrasse Tyson, not this one. No, he was in a different one. He was in a different one I almost used, but this one was good too.
You've almost certainly seen a periodic table of the elements. But have you ever wondered where those elements came from?
He was in a different
To
one I almost
understand their
used.
origin, first we have to look at what defines an element. An atom is made up of positively charged protons and neutral neutrons in a nucleus, surrounded by negatively charged electrons. The number of protons in the nucleus defines an element, but a single element may have atoms with a varying number of neutrons. These are called isotopes, and though these are all still the same element, they vary in their stability. Some nuclei are stable and require large amounts of energy or bombardment by other particles to transform into different elements or isotopes. Other nuclei are inherently unstable and will spontaneously decay. We begin our story with the Big Bang. As the universe expanded and cooled, the sea of fundamental particles began to coalesce, forming the first protons. And a proton is the nucleus of the first element on the periodic
Trying to
table.
fix it for her.
hydrogen.
Hold on.
In the first few minutes, a
Yeah,
few
no,
more
it's just
nuclear
being
reactions
weird.
occurred to create some helium
Yeah.
and very tiny amounts of lithium. At this point, synthesis of larger elements was put on hold until the inhomogeneity of the universe led to the formation of stars, which could become hot enough to allow for further reactions. Many stars start off small and are fueled by their ability to fuse hydrogen into helium, much like our own sun. Once their hydrogen fuel has been used up, stars which are massive enough go on to fuse together larger elements, while they themselves increase in size and temperature. But there is a limit to a star's ability to fuse smaller elements into larger ones. When small nuclei are fused together, the nuclear reaction releases energy, supplying the pressure needed to keep a large star from collapsing onto itself. But we reach a problem when a star forms iron-56. The nucleus of this isotope of iron is the most stable nucleus in nature, meaning that it can't be fused further to fuel a star. In other words, stellar nucleosynthesis halts at iron. At this point, the star has no energy to overcome gravity, causing it to implode and then rebound to explode in what we call a supernova. During a supernova, intense amounts of heat and gamma rays are produced. These gamma rays go on to break apart some iron nuclei into, among other things, copious amounts of neutrons. Intact iron then acts as a seed, capturing these neutrons and then decaying into new, heavier elements. Some of these new elements can even undergo nuclear fission to produce other ones. This process in a supernova is a primary one responsible for creating every element past iron, all the way up to plutonium. And since it is an explosion, all of these atoms are sent flying throughout the universe. But that still leaves a few more elements. Backtracking a bit, lithium, beryllium, and boron are not made in large quantities in stars. That's because these elements tend to be used up almost as soon as they are synthesized. Instead, they're made primarily by cosmic ray spallation, a process where high-energy particles collide with carbon, nitrogen, and oxygen, removing nucleons to yield these three smaller elements. And finally, every element larger than plutonium was made synthetically by scientists, though plutonium itself and a few smaller ones can also be man-made. In the end, all of these processes are responsible for creating every atom in the universe, including the ones that make up you and me and the entire Earth we live on. Now, understanding stellar life cycles and nuclear processes can be very complex, and this video just touched on the basics. If you're interested in learning more, feel free to ask questions below or check out some of the links included in the.
So it was interesting because in our whole physical science curriculum, we never got to a point where we talked about iron being the stopgap for the supernova, right? We talked about it becoming too massive, the star becoming too massive, but we never really got to a point where we were like, and because of. All right, so back to there. This won't go, will it?
These stars.
Okay, so this one's an important one to remember. Did any of you guys memorize this list yet? This is a list.
Sort of.
Oh, probably.
Carbon, hydrogen, oxygen, phosphorus, and then there's one more.
It's the
Sulfur.
first. It's the first 6 elements.
Okay, so this is going to be particularly important next year when we do biology, but these are the 6, okay? It's carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. And the way there's lots of different little mnemonic devices, but the one that I always learned was this one here, which, you can't see it because of them, says schnapps.
Oh, like the beer?
Yeah, kind of like, well, it's not spelled the same as schnapps, the liqueur, but it's schnapps, C-H-N-O-P-S. And if you can, Coley, Michael, you guys, did you need something? You good? Okay. The schnapps thing here, this is what you're going to see in pretty much all living things. There's other stuff going to be involved, but these are the big ones. So if you were to move on from here to organic chemistry, you would get really familiar with these guys. And organic chemistry is a whole different beast than this inorganic stuff we're doing right now. We're touching on a little organic this year, but organic chemistry has a lot to do with molecular structure, and there's a lot of stuff with rings. Get into all the rings, and it has to do with like whether molecules are left-handed or right-handed, and it gets it's interesting. So immediately after the Big Bang, temperatures were extremely high, and only what was the first element we're dealing with that was the first thing that could exist?
It just said energy in the book.
And oh, that's right, sorry, energy. Yeah, sorry. The next one is elements. So reading ahead. Energy. Yep. Okay, only energy could exist, and as it began to cool, then what was the first element?
So energy was converted to matter in forms of electrons, protons, and neutrons.
Right.
And as the universe continued to cool, these particles joined together the first two elements, hydrogen and helium.
There you go. Okay, hydrogen and helium. All right. Do you guys, any of you guys that have done physical science, do you remember about what happens in the sun?
Fire burns.
Right, but do we remember what's happening in there that's created, where the energy is coming from? Do you remember about the fusion?
Burning gas.
Well, we had,
Fission and fusion?
yeah. You have
Nuclear
your,
bomb, boom.
yeah, you have your
Split.
hydrogen and your helium basically coming together and breaking apart, and then there's energy involved in that bond breaking, bond creation, right? All right, so temperatures in the stars get high enough to fuse what?
Helium.
I don't see it.
Helium. Nuclei with another one forming elements of higher atomic numbers.
It
And
was
where do we get up
I
to?
almost forgot that one.
Where do we end up?
Yeah, 6 is the only one we did.
Yeah.
Okay, but what was the highest we could go according to the video you just watched? Iron, right? Okay, so massive atoms such as iron and nickel formed by repeated fusion reactions. That's all it is. Yeah, it maybe seemed like a trick question. What's the difference between fusion and fission?
Fusion is adding them together, and fission is splitting.
There you go. Yeah, okay, good. So there's this
You're
there's this Facebook page called Bad Science Jokes or something. I don't remember which one it is. It's one of the ones I'm in. But somebody posted the other day, you know, what are some of the dumbest things you've ever heard, or whatever, stupidest things you've ever been asked? And some guy on there said that somebody said to him one day in the conversation about, I don't even know how it came up, but did you know the sun was a star? And like the full-grown adult was dead serious. Did you know the sun was a star?
Really?
But it's kind of like that time
Did you know Earth's a planet?
we had friends over years ago when Cole was really little, and Cole was obsessed with ISS at the moment. And we were talking about ISS was going to pass over the space station. Yeah, and we were going to watch, because you can watch it if you've never seen it. It's awesome. Have you ever watched it? Yeah, we make a habit.
Only one.
Yeah.
You good?
Yes.
So anyway, we were talking about it, and she was like, what do you mean there's people in space right now? She had no idea either. She was a full-grown adult. She didn't know, Glenda. She had no idea there were people in space. Yeah. So when a massive star has converted almost all of its core hydrogen and helium into heavier elements, it collapses, blows apart, and that's what?
Supernova.
Supernova. Yeah, we did that last year. Forming elements heavier than iron. The nuclear reaction that, here we go. The nuclear reaction that changes one nucleus into another by radioactive disintegration or bombardment with other particles is called what?
Transmutation.
Good job. All right. So, what do you call the elements that we create as opposed to the ones that occur naturally? Synthetic. Good. All right. Now we're going to get into something interesting. The special equipment scientists use to create elements.
Particle accelerators.
Particle accelerators, right? Okay. Now
Aren't they kind of like those?
we're going to talk about some particle accelerators in a
Aren't
minute.
particle accelerators similar to the machines that like forensic people use that help get DNA out of blood by switching it around?
That's a centrifuge.
I know, isn't it kind of like that, but on steroids, because it moves, it spins.
Sort of, if you want to kind of go with that
Spins out,
analogy.
breaks things apart.
We're going to talk about some in a
That's what I
minute.
was thinking
They're
of.
cool. About what?
In a circle and went fast.
Oh, okay.
In the Flash TV show, he got his powers from a particle accelerator.
Did he? I didn't know that one. Okay.
You just like sit in one.
So there are 93
Explode.
naturally occurring elements, yet the periodic table has 113. So what's the difference?
The other 20 were man-made.
That's right. 93 occur naturally in Earth or space. The other 20 are synthetic. So why are there limits to the synthetic elements that cyclotron can produce?
There's a limit to the energies that can be reached.
Yeah.
Yeah.
Can you expand on it?
You can't go fast enough sometimes.
You can't go fast enough. And the reason you can't go fast enough
Yeah,
is
there isn't
because-
big enough energy supply.
yeah. So as you're accelerating the particles and they're mashing together, it's becoming more massive, right? So as it becomes more massive, it's going to require more energy to keep it moving. And we've reached a limit with our technology. That doesn't mean that maybe we can't figure it out one day, but we've reached a limit right now where we cannot accelerate them any faster than we currently can once they're massive, once they become more massive. So how does it accelerate particles? How does a synchrotron specifically accelerate particles to create synthetic elements?
It does that by timing the pulses to match the acceleration of the particle.
Yeah, can you think of an analogy of something, maybe something that came up in physical science? Think of the swing set analogy.
Yeah.
So think about pushing someone on a swing. You've got a kid on a swing and you're pushing them. If you time it right, when they get back to you and you push, are you going to get a better result than if you push when they're like halfway back? There's a timing, right? It's a beat. And that's exactly what they do. They push. They use magnets and electrical pulses, and their pushes are in sync to the acceleration. So that increases the acceleration. So basically, they get them moving faster and faster by taking advantage of the rhythm that they're using to accelerate, which is kind of a difficult concept. But if you think about the swing, it's sort of easier to conceptualize. So why is it difficult then to identify the heavy elements, the super heavy elements that are being created?
They last for less than a second sometimes.
Yeah, they're they're
Is it less
Boom.
than 100 of a second?
Yeah.
or
Less
yeah.
than 100th of a second. It was
Very
like
fast.
0.00.
Yeah, this should say few
0.01.
hundredths of a second, but yeah, they're super fast as they come through. So I wanted to show you, this is just an image, but I do have some cool stuff. So cyclotrons versus synchrotrons. Okay, cyclotron you could fit in this room. Easy peasy. Nearly every hospital around here has got cyclotrons. Cyclotrons are used for all kinds of things now. They use them very frequently now for stuff like proton therapy, which is a type of radiation they use for cancer, brain cancer specifically. So they used to do the X-ray therapy for radiation, and it would shoot the X-rays like all the way through the brain. Whereas with the proton therapy, they can really kind of narrow it down. So this is a pretty modern topical use for cyclotron. But you could stick a cyclotron in the middle of this room. And there are hundreds of thousands, if not millions of them all over the place, right? They're everywhere. They're common. Synchrotrons, however, these are your synchrotrons of the world.
Oh, wow.
That's it. Okay.
Wait, there's one in. Okay, so.
Mhm.
There's just one in the center of Roger. Just-
Yeah, it's kind of that one probably is scary. I don't know what's going on over there by themselves.
One United States.
And this one is probably, well, the ones in the middle of nowhere worry me. Like this one worries me. This one, what are they doing? No,
Is Africa mainland?
I don't
Africa?
see any in Africa. But here's the deal. I worry about the ones in the middle of nowhere. It's like,
Yeah,
what are you
the
doing
one
out there,
the one in
people?
the middle of Russia is-
And the one in the middle, the one down
is
here.
set in the sea.
Actually,
And the one down
in
here.
South America isn't that closed off. That's
That's true,
city.
yeah.
And Japan's just covered in
That's
that.
just
Japan,
good.
So anyway.
You can't even see Japan. You just see the dot.
So look at Japan. That's a really good point. They have a ton of them. So a synchrotron is absolutely massive. Massive. Like there are some pictures here where you can kind of see.
Yeah, I see.
But I'm going to show you some other pictures here because I'm talking huge. And let me go back to this. So synchrotrons, there's a very famous one. It's an older one, like from the 60s, older one. And yeah, they've been around for a while. And it's this one, CERN. And CERN is in France. If you read any of the Dan Brown, like Da Vinci Code and all that,
That's not the cyclotron.
there is a synchrotron in, no, that's not. Sorry, I should go this way. No, but there is,
Oh, wow, that's a big.
there we go. Yeah, there is, this particular facility is mentioned in, I think it was Da Vinci Code, maybe in Angels and Demons. I'm pretty sure it's Da Vinci Code. But anyway, so for example, this is the inside.
Whoa.
All right, so you can see like this is the big tunnel.
That looks like a
Is that
big
spin?
No, that's the tunnel they shoot it through. Yeah. It does but this, to give you some idea, this is a proposed site for a new one. Massive,
Wow.
really massive, not tiny by any means. I mean, this is a village. Look, this is a whole village right here.
Alice is a village.
Alice appears to be a teeny little village. So they're really, really big. And if you find, sometimes there are schematics of them on here. I saw some.
Like a bird's eye view of one from.
Oh yeah,
like,
there are lots of aerial shots. Like if I do just this, will pull them up. There's a ton of them. So for example, this is like a model of what one would be.
Yeah.
And this is not to scale because you can see little computers there. Definitely not to scale. But this is a real one.
Wow.
This is, I think, the schematic before they built
And I'm
it.
sure it's 1,000 times bigger in person.
It's a light source facility?
Yeah, I think Light Source is the company.
Oh, okay.
Because I was trying to figure out what that was about because it kept
looks like
popping
a-
up when I was looking these up.
Like a soccer or football arena.
They're huge. I mean, here's one, and this is a smaller one, but still can't stick it in a room, right? Big, 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 huge things. And fascinating that they can, that here's one here, how a synchrotron works, see? But here are, like it shows you here, they shoot this direction and it just whips around.
Shoots what?
It says here, there's energy boost here, ready, aim, light starts with an electron gun. Heated element or cathode produces free electrons which are pulled through a hole in the end of the gun by a powerful electric field, produces an electron stream about the width of a human hair that then whips around that massive thing, which is just crazy when you think about it, right? Then it says here, catch the wave, electron stream is fed into a linear accelerator or LINAC. High energy microwaves and radio waves chop the stream into bunches or pulses. The electrons also pick up speed by catching the microwaves and radio waves. Then they exit the LINAC and electrons are traveling at, oh boy, 99.99986% the speed of light and carry 300 million electrons. They are moving. Then you get a boost here. It says the LINAC feeds into a booster ring, which uses magnetic fields to force the electrons to travel in a circle.
Is that the fastest thing we've done?
I think
Have we
it,
ever gotten the light speed?
I think this
Oh.
might be.
Yeah.
I think it might be. Radio waves are used to add even more speed. Booster ring ramps up in energy, electron stream. So it says between 1.5 and 2.9 giga electron volts, which is enough energy to produce synchrotron light in the infrared to hard X-ray range. And then lastly is the storage ring. It says the booster ring feeds electrons into the storage ring, a many-sided donut-shaped tube. The tube is maintained under a vacuum, as free as possible of air or other stray atoms that could deflect the electron beam. Computer-controlled magnets keep the beam absolutely true. Synchrotron light is produced when the bending magnets deflect the electron beam. Set each of the bending magnets is connected to an experimental station or beam line. Machines filter, intensify, or otherwise manipulate the light at each beam line to get the right characteristics. That's, whoops, didn't mean to click that.
The beam line.
Yeah. So
Odd.
anyway, they are, I don't know what that was. I bumped it and now I can't make it go away. So anyway, they're huge, huge, huge. And I've never seen one for real. I would love to. I think that would be a really cool thing to see. But
How much does one of those cost, I wonder?
ooh, good. Yeah, I was gonna say billions is right. Good question.
Virginia.
Yeah,
in Hampton.
yeah. But I don't know. I wonder what they cost. Let's just randomly put this in and see what we get.
Many dollars.
They're usually multi-country consortiums, and they come together and everybody chips in a couple $1 billion.
What?
They're building another one right now. It's the big world.
It's really
Trade
damn
Center.
I don't know. I just didn't click it. There, what'd you say, Jace? They're building one?
Another one right now. It's gonna not even, it'll take like 10 years to finish or something.
Where's that one? Do you know?
Let's go up to the top for
In Europe.
Just looking here. So this one, 220 million, and that 5 years
That one's
cost
being
600. That's in
rescued closer.
Australia. Yeah. The Wikipedia in general says what? They're huge for sure, and they are expensive. That's a great question.
CERN costs.
Well, yeah, but CERN is so old is the thing. Because CERN's been around 5 billion euros. According to CERN, released oh, this is the new one. Okay, so this is the one that we were just looking at. Oh yeah. So I was reading about this yesterday. Remember the picture I showed you over the ground? They had a little circle on the ground, and like this is where we want to put it. So this is the one they're talking about building. So it says, yeah, tunnel would cost about 5 billion euros to build, plus another 4 billion for the initial lepton collider that could get going in 2040. An additional 15 billion for the Hadron Collider, that would replace the first collider and be operational sometime in 2050. I mean, geez, sorry, but I mean that's not cheap. Wow.
I think we all 2050. That's a while.
2050, but this is the one. She had some.
Jeez, man, why did you say that?
There were pictures in this one, I remember. They had some schematics of it. It was cool. I have to watch all. No, I'm just skipping it along. If I can.
Yes. Now just for the science, we wouldn't know.
Show me the pictures.
So at the moment we have the Large Hadron Collider, LHC.
With the LHC, which you discovery of the Higgs boson.
That's the particle responsible for the masses of all the other elementary particles. Discovery of the Higgs boson was a big deal. This is only the beginning of the story.
Think about Christopher Columbus looking for a westerly passage to Egypt. He set out to do something that was in the end completely different from what he discovered. But that discovery was the Americas, and it was of tremendous importance. And sometimes science is just like that.
I think if we stop exploring.
Oh, here it is. Here's the schematic part.
And surround the city of Geneva.
In places, FCC will go down to depths of something like 500 meters. It's an amazing job for civil engineer.
With the LHC, the beam is 1/3 of the diameter of a hair, 2,808 bunches. In each bunch, we have 150,000 million photons circulating, and when they collide, they generate only 30 photons. And in the FCC, we will have 7 times that quantity of photons.
If you want to look at things on a very small scale,
we have to increase the collision energy to design a machine that is 1 order of magnitude more performant than the present LHC.
The FCC would be the world's most powerful microscope. One always talked about proton-photon machines as discovery machines.
Colliding electrons and positrons, you're working at lower energies, but you can make very precise measurements.
There will be a lot of discussions on what the best.
It's so colorful, you know? I love it.
We will need all the people of CERN, but all the people also worldwide. Such a project can only be realized as an international global effort.
You can no longer do such science alone.
Science knows no borders.
I think science have very pure.
So this is the newer project, but you can look, and there are historic pictures of, I'll show you one real quick, and then I wanted to show you one other quick thing. So if you look like CERN, because it is older, I think it's 1960 something.
That's crazy.
Yeah, there are pictures of it. Here you go. Like,
Pictures, black and white.
these dudes are digging the tunnel. I mean, whoopsie, whoops.
The LHC started construction too,
Yeah, that's what that was.
but it's been paused several times because they run out of money. It was an enormous cost and money suck.
I'm sure.
They just run out of money and then they have to go, ask for more.
Mm-hmm.
They stop building and everything.
A little more, please.
Yeah, can we get a little more money?
6 months later.
It becomes a big port project too.
So you end up with these dudes digging tunnels. All of old pictures of that, and then there's definitely like these guys looking at the site, and I mean it's been a while. It's been a good while that CERN was built in. I want to say it was 1960.
Not even close.
No. Before that, there was one before that. This is here you go. CERN began in 1954 when they made breakthroughs in both particle physics and technologies. And then they keep,
Wonder if the nuclear
they
bomb
keep
had to do with
updated because they keep bringing things. So there's your LHC that Jason was just talking about, the Large Hadron Collider. Okay, so then this is the other thing I want to show you. So when we were talking about the elements that the noble gases, how they're totally stable, they're cool by themselves, right? And then we were talking about how you have the halogens, which are super reactive, and then you've also got your alkali metals, which are not often seen in pure form. They're usually seen combined with something else, right? You don't usually see pure sodium because it's super unstable. So this guy is going to take a pound of sodium and throw it in water. Now, I played this for the group earlier, but I couldn't get the sound to work. So I'm hoping there's no bad words in the sound because, all right, so this guy is going to throw a pound of pure sodium into a pond.
I'm recording it, and you're still wants to throw it in. Oh, sure.
So you're going to have to make that pure sodium in a lab because you're not going to find it in nature.
You can already tell where they're going.
Hold on, wait. This is sodium.
That's fine.
So remember, it's very reactive, right? Because it's used to being with something. All right, so here we go.
Whoa. Dang.
It's like a volcano. But isn't that crazy? How it's just, you're never going to find it by itself in nature because that's what it would do. So it's combined with other stuff all the time. Because yeah, never a good thing to be alone when you're that reactive. All right, so I'm going to do this, and I'm going to take it off there. And would you guys like to do a quick test review? No, you don't want one. You don't care about a test review. I kind of think you would. Go away. Boom. Sometime today. All right, awesome. Okay, so I'm going to go to a quick test review for you guys and see if this helps you study up a bit. All right. One second. So you have your notes out if you need them or whatever might help you. So we're not quite there. Your test is due next week. So let me see. So your test is going to be a total of 4 questions. Dun, dun, dun. 4 questions. And the first one is asking you about families. If you were, families and groups, remember, are the same thing, right? So if you're using the word family, you can use the word group interchangeably. And why did that just do that? Sorry. Okay, no screen share on, right? Screen share is not on. Excellent. Okay, so if you're using those words interchangeably, if I were to ask you, to what family does strontium belong? What would you be able to answer that? What would it be? Look up there.
Transition metals?
No, strontium is SR.
Then it would be an alkali.
There you go, alkaline metals. What if I said, calcium?
Alkaline, I believe, if it's Ca.
First group.
Yep, alkaline earth metals, same thing. We were right there. Okay, how about if I said, I'm looking, silicon?
Okay, silicon is a S, so what is that? Green group.
Non-metal.
Yeah, no.
Si is silicon. Si.
Then it'd be a metalloid.
Metalloid. Okay, good. Good. All right. Now, if you want to look at your periodic table for these questions, that's fine. I don't expect you to memorize where everything is. That's craziness. So it's okay to be able to look at it. You just have to be able to tell me, I need to make sure that you can understand how to read it. Okay, which of the following is, let's see. So which of the following is an alloy? Is an alloy? Gold, nickel, or brass?
Brass.
Okay, good. What is an alloy?
Mixture of two or more metals.
There you
or
go.
metal with a non-metal.
And why would you need an alloy? What's it for?
To make things stronger or less reactive.
To give a specific characteristic.
Yeah, whatever you're looking for, right? Absolutely. Okay. What's a property that all noble gases share?
Very unreactive. and
Yeah.
Very good in neon signs.
Very unreactive, very good in neon signs. Okay, there you go. All right. Why are they unreactive?
Because they have a full outer shell.
Yeah, their valence shell is full. There's no vacancy in their valence shell, and because of that, they're very unreactive, right? All right, and then let's see. If I were to give you some of the heavy metals down there on the very, very bottom line, with the actinides, for example, and I were to give you some of the heavy ones, why would they be on the table if they're not found on Earth naturally? Because they're synthetic. And what about some other ones that maybe aren't synthetic, but you can't find them on Earth? Well,
Because they're in supernovas.
they're in space somewhere, right? In stars, whatever, in
Or
space
they're
somewhere.
alloys, divided molecules, things like that.
Those aren't elements though.
Right.
Well, they might be part of an element, but they might be an element, but they might be found in the molecule.
Now what, say again? I want to make sure I understood
Might
it.
be an atom, but you might not find them in a pure state. Or
Okay, yes,
or
you
there's
may not
some
find them by
parts found.
themselves. Yeah,
They can't be found in the crust, but they might be found in the core of the earth.
correct. Correct. Okay, so then I'm going to put it back up on the TV in just a second here. Oh, go back. So many little apps open down here. It's crazy. Okay, I'm going to share my screens again. Okay, we're going to go over to that in a second. Now I got to go back to, why isn't it right there at the top again? Okay. Reconnect over here to the TV, 1 second. And just take it. There we go. All right, so let's see if we go to, it should pop up there in a second. Please pop up. Don't be weird. Do your thing. Connecting, 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 connecting. There you go. Okay, so if I were to open this here, and I'm gonna draw for you, but I have to move this box out of my way because I can't see all my tools. All right, so say let me pop it off. Easier to draw in my lap. Sorry, you're looking at the ceiling. Okay, or up my nose, but I have a mask, so you're at least not looking at my nose today. So look at, for example, let's look at fluorine, okay? How many, what's the atomic number for fluorine?
9.
9, okay. So that means it has how many protons and how many electrons?
9.
Okay, good. So let's do it this way. Let's do, come on, do your thing. Neutrons, we're gonna have,
F, by the way, for the.
did I actually write the L? Because I was gonna write the word and then I changed my mind. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9.
Does that count as a brownie point?
There we go. No, because that was just gonna change my mind. All right, those are gonna be our neutrons, okay? Let's do our protons. We'll make them green. 1, 2, 3, 4, 5, 6, 7, let me make him bigger. 8, 9. Okay, there's our nucleus.
Would you like me to go
We-
see
we
how
cool with
many
that?
neutrons there actually are?
No, there's about 9. It's about right. All right, so let's think of this for a minute. All right, what are gonna be our What are going to be our energy shells? Who can do that for me?
2 and then 7.
Well, we've got what? We have
11.
1, S, 2, then what? 2, S, 2, right? You following me? 2, P, how many? 2p6 is supposed to be an S. I'm trying to make it legible. 2p6 would be right, but how many electrons do we have in fluorine?
9.
We have 9, so it's going to be 2p what?
5.
2 plus 2 plus 5. Now, how many electrons do we have? Here. 2 plus 2 plus 5 is?
9.
9. Good. So that means we've got fluorine, right? That's what it's going to be. You following that or no?
Yeah.
Okay. So we have 1, 2, and you remember that this other one is not really round, but I'm going to draw it like a Bohr model. Okay? Now.
Oh, I was talking about that. Can I please turn off the video?
Okay. So how many do we have in this one? One. I made you, don't do that, I made you red. I totally made that red and it just didn't like me. Go back. There. 1, 2, correct? 1, 2, correct? All right. Whoops, not correct. I put them on the wrong one. See, this is what happens. when you're late. Exhausted from the dentist yesterday. He wore me out. I'm telling you, just going there wears me out. I can't even like think straight when I leave the dentist. Okay. Here are these two. That's 2s2, 1s2 and 2s2, right? 2p5. Okay. 1, 2, 3, 4, 5. But then what? We have one more space where we don't have one, right? You see? Because we're supposed to have, how many would fill it? We would have 2p what? What's the total number you can have in that shell? 6, right? You can have 6 in 2p. Because we can have 2 in 1s, we can have 2 in 2s, and we can have 6 in 2p, but we don't have 6, we have 5, because this is fluorine. If it were neon, how many would we have?
There would be 6 in that.
There would be 6, right. So if there was one here in this little empty hole, this would be neon, right? And that's why it's non-reactive, because there's nothing going on, it's full. But right here, this is why the halogens are so reactive, because it wants something to fill this hole, to make it stable. So it's ready to snatch onto an electron from just about anywhere. So what's a good example of one of the halogens? How about chlorine? What's the number for chlorine? Let me just do it this way. Yeah.
The what number?
What's the atomic number for chlorine?
17.
Chlorine, 17. All right, so then tell me. We're going to have, hold on, trying to make this more legible. We're going to have 1s1, right? Somebody get a book out. Tell me what's next. 1s2. I'm sorry, 2s2. I wrote 1. Sorry, 1s1, 1s2. God, I cannot write today, guys. 1s2, 2s2, 2p6. Now, how many do we have? We have 10. We need 7 more. Where are they going to go? What's the next one?
1, right? Did you say we can get 10?
What's the next energy shell? Where's your book?
3s.
3.
That's
Ah, everybody's like, oh boy. Look on page. I'm going to tell you where to go. Look on page. No. Well, actually, look on 119. So you said 3s, right? 3s, what? How many fit in an S? 3s2, right? What's going to come after that? So we have 8, well, 10, 12. We need 5 more. Where are they going to go?
Is it 3s3?
So 3s2, 3p what? 3p3. Look here. Who has it? Who has 119?
I
Do Do anybody have it? You look. Here, I have it. Look here. Follow this. So we're on, well, don't use my stylus. All right, what have we got? You see, I'm turning, whoop. Sorry, I'm turning that camera around.
1S2.
All right, you following? So you got, whoopsie. I have my tablet here. I'm trying to get the camera where they can see. Okay, there you go. So we had our 1S1, 1S2, 2S1, 2S2, 2P goes all the way to 6, correct? 3S1, 3S2, what's next? 3P, going to 6. Okay, so 3P. And how many do we have in 3P? 10, 12, how many do we have? 5 instead of 6. We should know this just by the fact that, what was fluorine? Fluorine's one above chlorine. How many did it have in its valence? It had 5. So if it had 5 in its valence, then the one below it is also going to have how many in its valence? 5, because everybody in a period, up and down, I mean in a group, up and down, always has the same valence. So there's our 5 again. So everything, remember all of the elements in a group or family, group really, are going to have the same number of valence. So if fluorine had 5 in its valence, then chlorine has 5. How many is, oh, I can't see them, iodine going to have? 5. How about bromine? 5. Okay, good. Chlorine needs to combine with something that has how many valence electrons?
5, right?
It has 5. What does it want?
6. So it needs
6. So what does it need to combine with?
a 1.
Something that has 1 valence electron. What has 1 valence electron over there?
Alkalis.
Oh, yes, the alkalis. Lithium, sodium, potassium, rubidium, cesium, francium. Okay. When we did our lab a couple weeks ago, when we were trying to check for the spectra of different metals, right? Remember, we did the flames? Okay, those were metals we were testing. Which metals were they? Alkali metals, because they all had combined with one of the halogens to make a salt that we could burn. So lithium, chloride, sodium, chloride, potassium, chloride, right? That's what we had. Okay, so if you look at it this way, if this is your chloride and this is your sodium, how many valence electrons do you have in your chloride? We just said it. 5, right? So let's just do him. Actually, I'll make him go closer in a minute. We have 5. 1, 2, 3, 4, 5. But we want how many?
6.
We're missing 1. Where are we going to get him from?
Another.
Which one are we going to get him from? Let's say we like sodium,
There's an alkali, right?
right? And sodium is going to have how many in his valence? He's going to have 1. And what do you know? How do you end up with there? Ta-da! You end up with exactly what we were saying, right? That's why you get those halogens combined with the alkalis. Remember, that's all we had in the lab. All we had were halogens combined with alkalis, one after another. And that's why, because they're going to line up that way. Neon is not going to combine with anything because neon is going to have a totally full. So will all the other guys over there, argon, all those fellas, xenon, they're loners.
Just say like, how did you know to skip?
What you need, Abby?
All right. I'm still confused with the 1S2, 2S2, etc.
Okay, so it's just a pattern and it never changes. And it's a good one to memorize, at least up to maybe the 2nd or 3rd P, because it's always the same. But if you look, you can find it in multiple places. Why are we going to my website? I didn't ask you to do that crazy thing. So whoop, did it click the right one? Electron shell configuration. There it goes. Why does it keep going away? There it goes. Oh my gosh, y'all, my fingers are fat. There, I clicked the right one. I'm using my tablet, so it's like, it's totally goofy. So yeah, if you, I can't see the top of my screen because it's being weird. But if you, anywhere you go, you should be able to find the list. And like, here's a great example of it right here. So this is the order that they fill in. 1S1, 2S2, 3S2, 2P6, 4S2, 3, I clicked it.
Are
I
you
accidentally touched
sharing-
it.
Are you supposed to sharing the screen? Because I still see the slides.
Oh no, hold on. Sorry. It makes me do this thing where I have to stop and start over.
Screen.
No, it's not just that. It's about, can you see it now?
There it is. Awesome.
Yep.
Thank you.
It makes it, even though I'm sharing my screen, if I go from one app to another, I have to go back and tell it to share that screen.
Open up that screen, yeah.
Hmm?
The one where you just chose the app on, open it again.
What do you,
Instead of choosing an app,
yeah,
choose the one that says screen.
yeah. I can do that too.
That's how you stop.
I did that before though, and it still did it weird. I don't know. We can go either way. You still see it now?
We got it now. We
Oh.
got it.
All right, so
I got it. Thank you.
this is always going to fill, I don't know how I can't get this guy out of my way. So I can't see what I'm doing fun times. But anyway, it's always going to fill in the same order.
Okay. I
Which
didn't
is
realize.
convenient because if you, okay, there's my mouse back. It's like, oh, there. I can't, this little thing that you, I don't think you can see it. Can you see the thing that says connected to living room TV?
Yeah.
Okay, yeah, it's like messing up my stuff. So it'll always be the same way.
Just press control. Switch between the two.
You are such a, like a computer geek, Michael.
Kind of built one.
I know you kind of built one. Michael has built a computer. He knows everything about them. I don't. So anyway, it's always going to feel the same way. And if you memorize them, there's like all kinds of videos. There's probably songs or whatever. But if you memorize them, it makes it faster because then you don't have to look it up every time. But they always, there's like a gazillion images that you could choose, whichever one works better for helping your brain work. But they're always going to fill, like level 1 is always going to be 1S, level 2 is 2S, 2P, level 3, 3S, 3P, and they're always going to fill. Do you remember like a couple weeks ago when I was doing the thing where I was laying one image over another?
Yeah, the weird shapes. Yes.
Yeah. I actually found some strange graphics for that the other day where they actually had a little animation of that. Like that would have been nice to find before I created it on my own, but it does exist. So, but that's how they fill, the same time every time. So when we get into what bonds with what, it's really necessary to understand what's in the valence. So it's easy to remember, you know, if you look at the periodic table, it's easy to remember that everything going vertically has the same number of valence and everything going horizontally has the same number of shells. All right. Does anybody have any questions about anything, or are we cool for this for now? We are about to hit October in like 2 days. So that means Tinker Day at some point. Be ready. Get you some donuts, stick them in the freezer because then they're ready. And then also beyond that, I think everybody here has gotten back to me already about second semester, whether you're online or, yeah, so should be good to go. And I'm gonna do my lab shopping at the end of the week, which I'm kind of very excited about because we have some fun things coming like desiccators and cool business, desiccators. Abby, Shannon, Alex, I don't know where Kai went. Anybody have any questions? Are you good? Are you feeling better, Abby?
Yeah, it's stupid cough. It's not going away.
I'm sorry. That's a bummer. I hate that. That's no fun at all. Yeah, that's no good. I don't enjoy that. Yeah. They all said you have the void. The co-void. Oh yeah, okay, y'all are so helpful. The Rona. She got the Rona. No. I had to take Drew for that Rona test. It wasn't terrible. They just did the nostrils. They didn't do his whole head. They didn't. So scary.
Alan has to take one 5 days a week to work.
Oh, he has to take it how often?
Every day, 5 days a week.
Are you kidding me?
he has to, they send a box of 5 every Sunday, and then they're labeled, and then he takes it and overnights it in order to be able to work.
Oh,
So
wow.
we're for sure clear. We have more tests than anybody. We hoard tests.
Crazy. Did you hear what she said? So she said Abby's dad has to do a test every day for 5 days in a row in order to work. So
Is it the all the way one?
yeah, is it the brain tickler or is it just the
No, he spits into a cup like a DNA test.
Spits. Okay.
But the
That's
best part is he doesn't work 5 days a week for the same company. So for one company, he works like Monday and Wednesday, and he has to report to Atlanta on Saturday and Tuesday to get their COVID tests. But for the other company, they
Nice.
send us 5 tests a week, and he has to overnight those. So he actually takes like 13 tests a week.
So he takes 13 tests a week because he's working for 2 different companies. I haven't seen anybody do the brain tickler, but we have a really dear friend who's doing IVF cycles, and she called us on the way to get her test because she had another cycle that week, and they made her do the test. So she had us on speakerphone, and she's like, "Hold on, guys, I got to stop here a minute and get another one of these tests." So she leaves us on speakerphone while she's getting the brain tickler deal. And she's like moaning and groaning and half crying, and we're listening to it, and we're all like, "Look, gosh,
Dang.
it was
IVF
torture."
isn't pleasant anyway, much less having to have that too.
It was straight up torture. Like just listening to her was torture. So I cannot imagine going through it. Well, all right, if y'all are good, I'll spring you about 10 minutes early. Let everybody take a break before Senora Jackie files in here. And hopefully we'll see you next week, Abby. You feel better.
All
You
right,
too,
bye.
Shannon and Alex. And I don't know where Kai went, but I know Sydney's coming back in a couple weeks. And Kai said probably next semester. So we're filling up. All right, y'all. Later.
Bye.
Bye.